Okay, this unit is called Work, Power, and Energy. We've already looked at work and power, so that leaves us one left, energy. And it's not just any type of energy that we're looking at in this unit. It's called mechanical energy, as opposed to like nuclear energy or solar energy or chemical energy. Mechanical energy, its definition is the capacity to do work. Capacity to do work. And so we would say that an object has mechanical energy if it has the capacity to do work. If it because of its position or its motion, it has the ability to do work. Okay, and remember, work is applying a force over a distance. Okay. Now, so as I mentioned at the beginning, there are all different types of energy. So as you go on in your physics and chemistry life, you'll run into thermal energy and sound energy and electrical energy and solar energy and wind energy and chemical energy, okay? But here we're specifically looking at mechanical. And there are three types of mechanical energy that we're going to look at in this unit, okay? But first, when work is done on or by, we're going to say a system, and a system might be you. You might be the system, and you're doing work on the garbage by picking it up and carrying it outside. Okay, so when work is done on or by a system, work is done on or by a system, energy is needed. In other words, you can't do work if you don't have any energy. So when someone says to you, take the garbage out, you might say, I can't do that, I don't have the energy. Okay? So when work is done on or by a system, energy is needed to do that work. To do that work. And the total energy of the system is changed. And the total energy of the system is changed as a result. So if you're the one doing the work, you're going to be losing the energy. If the thing that work is being done on, it's going to be gaining the energy. Okay, so object doing work loses energy. Object that work is done on gains energy. And when gains energy, and I'm assuming positive work here, not negative work. Okay, so clearly from this you can see a transfer of energy takes place from one object to the other. And in perfect ideal conditions there would be no energy lost. Unfortunately, in real life there is energy lost. So the work done by one object should equal the change in energy. Okay, and as we go through the three different types of energy in the next 2 days, we'll keep coming back to this because it's true. No matter which type of mechanical energy we're looking at, the work done will result in a change in energy. It might be a different type of energy in each case, but it'll still be an energy. All right, I think you'll understand as we keep going. So the first type of mechanical energy we're looking at is a type you met in last unit. It's called kinetic energy. And if you remember, all energy is a capital E with a subscript to denote which type. So kinetic energy is E with the subscript K. And kinetic energy is energy of motion. So any object that is moving is going to have kinetic energy. Okay, the two things that kinetic energy depend on are mass and velocity. And the equation is simply 1/2 mv squared. This is our equation for kinetic energy. All right, if we look at our units, they're going to be kilograms and then meters per second that gets squared. So kilogram meters squared per second squared. Well, and we know a kilogram meter per second squared, we know this is a Newton. So this is really a Newton meter. And what we learned with work was that joule is the name for a Newton meter. So not only is work measured in joules, but so is kinetic energy. And that should make sense. If the work being done on an object is equal to the object's change in energy, then the units must be equal. Okay? Using this equation is pretty simple. Fill in the mass, fill in the velocity. The squared only goes with the v. Okay, so you square the v, then multiply it by the mass, take 1/2. So if we go back to work done, we know that work done is equal to F delta D cos theta. And let's assume that theta is 0. Okay? Well, we know that F is equal to MA. So then this would become MA delta D cos theta. Oh, wait, I was taking the cos theta out. MA delta D. And we know A is equal to VF minus VI over delta T. So if we fill that in, it becomes M brackets VF minus VI over delta T times delta D. But this delta D over delta T is really V average. So W equals M VF minus VI times V average. But V average, average of anything, is equal to the two things added together divided by 2. Don't panic, I'm just deriving something for you. VF minus VI, so filling this in for V average, it would be VF plus VI divided by 2. So I'm going to take this 2 out front, so it'll be 1/2 m. And then, of course, we have to FOIL these, right? Multiply the first, so it'll be VF squared. Outer will be plus VF VI. Inner will be minus VF VI. And last will be minus VI squared. So these two middle terms cancel each other out, and we have W equals 1/2 m, and in brackets VF squared minus VI squared. If I multiply through, W is equal to 1/2 m VF squared minus 1/2 m VI squared. Work done is equal to change in energy, right? And that's what this is showing you. This is the change in the kinetic energy. Remember, change in is always final minus initial. So if there's a cart going rolling across the floor and you push it in the direction that it's moving, you're doing work on it, and as a result, you're going to change that kinetic energy of the cart. It's going to start going faster if you're pushing in the direction of motion, or slower if you are not. So, and remember, work done is equal to F delta D cos theta. So there's going to be a few homework questions or practice questions tonight with just this guy, and then a couple with this one where you have to find the work done and then set it equal to the change in energy. Okay, so that's kinetic. The second type, and we're not going to do all three today, we'll just start this second one. The second type is a potential energy. And so before we start it, we need to talk for a minute about what potential energy is, because there's a whole bunch of different types of potential energy in the world. And potential energy is really exactly what its name implies. It is energy. An object that has potential energy has energy that's stored in it that could be used to do work. So potential energy is stored energy. And a test to see if an object has potential energy stored in itself is to release it. And if you release an object and it moves, then it means it had potential energy. Okay, so in different types of potential energy, they're all stored.